Hi everyone, and welcome to this special series of A-Level Math in Trigonometry. My name is Emmanuel Olega and I'm a math teacher and a software engineer. Are you an A-Level student in Senior 5 or Senior 6 and you've been struggling with trigonometry knowledge? Oh, you're actually in the right video. I want to encourage you that if you stick with me to the very end, by the end of this video, you'll be very good at your A-Level math trigonometry. So this is going to be a special series where we're going to be covering the whole topic of trigonometry. I encourage you, if you're new to this channel, feel free to leave a like on the video and then tell me below in the comments if the video really helps you. And then later on, if it helps you and it proves very helpful, feel free to share it with all your friends and relatives. Alright, so without wasting time, let's get into today's trigonometry video. So welcome to this outline that we actually have here. So basically today we're going to be covering trigonometry. So this is where we are right now. So today's topic is going to be based in trigonometry. So I encourage you to just follow along. As we do the different numbers, I'll make sure that there will be a lot of examples for someone to follow along. And a lot of the examples will actually be UNEB questions. And this will be very helpful for a student who is pursuing their UNEB either in Senior 5 and Senior 6. As the student prepares themselves, it will be very helpful as they follow the examples. So I've actually done this purposely to help such a student in Senior 5 and Senior 6. So I encourage you to just follow along. If you can, get a book and follow along and do the examples and practice with me. I also encourage you that at the end of every single subtopic, there will actually be a small exercise, some trial questions that you can actually practice along. So just make sure to do those examples, and this will help you to progress faster as we move through this course of trigonometry. Alright, so today we're going to begin with the introduction to trigonometry. So you may ask yourself a question: what is trigonometry? So trigonometry is the study of the relationship between side lengths and angles of triangles. So what happens is there's actually a relationship between the different angles at the different vertices of every single triangle and the lengths of the sides of every single triangle, as we'll actually see as we practice through. So as you're saying, there are actually 4 kinds of triangles. So what are they? So they are right angled triangles. I think we know what a right angled triangle is. This is an angle where one of the vertices or one of the sides actually has an angle of 90 degrees. And then we also have equilateral triangles, and these are triangles where all sides are equal. So that means angles at each vertex are equal to 60 degrees for each single side. And then we also have isosceles triangles, and these are triangles where 2 sides are equal. And then we actually have scalene triangles. Now scalene triangles don't have basically some of those rules. So a scalene triangle has all sides having different lengths and all sides having different angles. So what we'll actually be doing is, in this very first phase of trigonometry, we should actually be looking at these first 3 triangles, and then I'll first keep and hold on to the scalene triangles until the very end of the course. So as we follow along, we'll actually first measure on these 3 as we progress, and we shall do scalene triangles at the end. So that is what trigonometry is. Alright, so let's start with right angle triangles. So we said these triangles have one angle equaling to 90 degrees. They also have a hypotenuse, which is the longest side. And it says for this test, we shall call one of the angles theta. Okay, so this is an example of a right angle triangle. As you can see, we actually have the side which has the angle theta, and this is the side or the vertex that actually has an angle of 90 degrees, and this is actually an unknown. And then we actually have sides A, B, C. As you can see, we actually have C as the hypotenuse, which is the longest side of the right angle triangle. Then we actually have B as the side that is opposite to the angle theta that we actually created, and then we actually have A, which is adjacent to the angle theta. Alright, so from Pythagoras theorem, I believe we remember that A squared plus B squared is equal to C squared. What that means is, when we are dealing with finding all the sides, we can actually square A and square B, and the total of the squares of A and B will actually be equal to C squared. So we're going to have this as our equation 1. Alright, so if you remember, there is actually a formula called SOH-CAH-TOA. So this SOH-CAH-TOA enables us to remember how to find the value of theta using sine, cosine, and tangent. So what happens is, when we use sine, we actually follow the rule of opposite. So when we actually find the value of theta, we actually follow the rule of opposite, which is the opposite of it, over hypotenuse. When you actually want to use cosine, it's adjacent over hypotenuse. And then when we want to find using tangent, we should actually use opposite over adjacent. So this will make more sense as we do different numbers. But as you can basically see, sine theta is equal to opposite over hypotenuse, and that's why we have OH. OH means opposite and hypotenuse. So that will actually help you to memorize and remember them as we follow along. So using sine theta, we can actually see opposite over hypotenuse. The opposite is equal to B and the hypotenuse is equal to C. So we have B over C. And then we actually have cos theta. So cos theta, we said, is AH, which means adjacent over hypotenuse. And that's why we have it there. So the adjacent of this angle theta is A, which is A. And then we actually have C as the hypotenuse. That's why we have A over C. So as you can see, if I actually rearrange these, because I have now cos theta is equal to A over C and sin theta is equal to B over C, if I rearrange these, I can actually have B as being equal to C sine theta. And then I can also have A as being equal to C cos theta by just cross multiplying. Alright, so what I'm going to do next is I'm going to substitute the values, because now I have B is equal to C sine theta. I'm going to substitute the values of B and the values of C into the Pythagoras theorem equation that we actually have right there. So when I substitute into equation 1, I'll have C cos theta squared plus C sine theta squared is equal to C squared. Alright, now we're going to continue from there. So as you continue, you actually see that we actually have the same equation. So what happens is the square will actually enter and I'll square both of the items inside the brackets. That's how I have C squared cos squared theta plus C squared sine squared theta. That means that the square is squaring every individual item in the bracket. So you actually remember that from algebra is equal to C squared. So next I'll actually factorize out the C squared. So factorizing the expression, I'll pull out C squared from this equation and I'll actually have it outside the brackets. And then as you can see, next we'll be able to cancel out this C with this. So I can divide both sides by C squared, which will leave a 1 here, and this will actually disappear. So I'll remain with an equation cos squared theta plus sine squared theta is equal to 1. So this is going to be the very first equation that we actually derived. So this becomes a true statement that cos squared theta plus sine squared theta is equal to 1. I encourage you to memorize this because this will be very helpful in all the different things. It's going to be a basic imperant expression as we work in trigonometry. Alright, so this is going to be the first expression. So as we proceed, I actually want to show you some reciprocal identities that will be helpful for you. You should also know that tan theta is equal to sine theta over cos theta. I encourage you to memorize that. And then cot theta is equal to 1 over tan theta. So that means cot theta is the inverse of this. So that means we can also say that cos theta is the same as cos theta over sine theta. And then we also have sec theta as being 1 over cos theta. And then lastly, we actually have cosec theta being equal to 1 over sine theta. I encourage you to memorize these identities that we actually derived here because these will be a foundation for trigonometry. Alright, so let's continue from there. So next we'll say we can derive Pythagorean identities from equation 2 by choosing to divide both sides of the equal sign by either cos squared theta or sine squared theta. So we're going to derive other new identities from the equation we actually created, the equation cos squared theta plus sine squared theta is equal to 1. And we're going to do that by dividing both sides by either cos squared theta or sine squared theta. So let's start with dividing both sides by cos squared theta. So we actually have our equation here, cos squared theta plus sine squared theta is equal to 1. If we divide both sides of the equal sign with cos squared theta, we actually have it looking like this. And then we actually have this separating and being divided individually by both of these numerators. And what we'll have is this. Okay, and actually as you will see, when this and this will cancel and we'll actually have 1, and then when this and this divide each other, remember we've just said that tan theta is equal to sine theta over cos theta. So since we have a square of sine theta and a square of cos theta, it actually means that these actually become tan squared theta. And then on this other side, we actually have this being sec squared theta because we said 1 over cos theta is equal to sec theta. So since the cos is squared, we'll actually have sec squared theta. And then we'll actually have this new equation that 1 plus tan squared theta is equal to sec squared theta. So this is also true in this case. So what happens when you divide both sides by sine squared theta? So the same thing, we actually have our equation cos squared theta plus sine squared theta is equal to 1. When I divide both sides by sine squared theta, I'll separate the sine squared theta between the different numerators, and what happens? So cos squared theta plus over sine squared theta is like the inverse of tan, which is equal to cot squared theta. And then this and this will cancel and will remain with a 1. And then right here, remember that 1 over sine theta is the same as cosec theta. But since we have the sine being squared, this will actually be equal to cosec squared theta. And then we'll actually have this new expression. Cot squared theta plus 1 is equal to cosec squared theta. So I encourage you to memorize all these. The reason I put them in yellow boxes is because they're important for memorization. And this will be helpful for the future numbers. Alright, so that's it. So let's move on to another kind of triangle. So we're going to move on to the equilateral triangles. And what are equilateral triangles? We're saying these are triangles where all sides have the same length. It is also true that each angle is equal to 60 degrees. Remember that all the angles inside the triangle total to 180, and then if it's equilateral, it means all sides or all vertices have the same angle, which is literally 60 degrees. So this is what we have here. So this is an equilateral triangle having all sides being equal to 2, 2, 2. And then what happens is, in this case, is every angle is 60 degrees. What happens is I've divided it from the middle. Then dividing it from the middle means that this portion here will actually be equal to half of 60, which is 30, and this side is equal to 30. And then what happens is, since I've divided it, it means that this portion here is divided into two parts. And since from here to here the side length is equal to 2, that means this portion is a half of 2, which is 1, and this portion is also half of 2, which is 1. And then the other sides remain as 2. Now this root 3, we're going to see how we actually derive that. So remember, from Pythagoras theorem again, let's follow let's use this other side. So it's, imagine you're actually using this right angle triangle that you can actually see right here, which has an angle of 60 here, a 1 here, and a 2 here. So from Pythagoras theorem, we can actually see that so actually these 2's okay, so this 2 is actually the hypotenuse, and then this is this side, which is the opposite, which we're referring to as, which is B, is actually unknown at the beginning, but with Pythagoras theorem we know that this is 2 and this is 1. So I'm showing you how we derive this root 3. So you can see at 1 squared plus, let's imagine this was B before we got the root 3, plus B squared is equal to 2 squared. Then what happens is we actually have 1 squared plus B squared being equal to 4, and then we can actually see that this, since this is equal to 1, we'll actually take this 1 to the other side of the equal sign, which means 4 minus 1, which is equal to 3. So we have B squared being equal to 3. And then when we root both sides, we actually see that B is equal to root 3. And that's how we got this root 3 right there. We can also see that if we say sine of 60, if we choose to get the sine of this angle here, we actually see at sine 60, which means opposite over hypotenuse is equal to root 3 over 2. And you actually see that this is true when you press it on your calculator, that sine 60 is the same as root 3 over 2. So this is important for memorization, because root 3 over 2 gives you the exact answer. And then you can actually see that cos 60 is also equal to a half. And remember, at cos of an angle is adjacent over hypotenuse, which is this adjacent, which is 1, and then the hypotenuse, which is 2. That's why we have a half. So cos 60 ends up being a half. We can also see that if we were to look at it from this side, so let's take this 30 here. So if we were to get the cos of 30, what is the adjacent of the 30? The adjacent is root 3. And then what is the hypotenuse? The hypotenuse remains 2. So you can actually say that cos of 30 becomes root 3 over 2. And then what happens is, if we look at sine 30, and remember sine is opposite and hypotenuse. So what happens is, what's the opposite of this 30 here? The opposite is 1, and then the hypotenuse is 2. And that's why we actually have sine 30 as being a half. So I encourage you to memorize all these. This will be helpful in future calculations. And this is how we derive the values of sine 60, cos 60, cos 30, and sine 30. Alright, so let's move on. So as you continue through that, you can also see that tan 60 is the same as root 3 over 1. Remember, we get tan by doing opposite over adjacent. So the opposite of the 60 was root 3, and then its adjacent was 1. That's why we actually have root 3 over 1, which ends up being root 3. So tan 60 is equal to root 3. Then we also have tan 30 as being 1 over root 3. Remember that the opposite of the angle 30 was 1, and then its adjacent was root 3, which means opposite over adjacent. That's why we actually have tan 30 as being equal to 1 over root 3. So I encourage you to also memorize these. This will actually be helpful in future calculations. Alright, so let's move on from there. So next we move on to the isosceles triangles. And we're saying these are triangles where two sides have the same length. It is also true that two angles are equal. In this example, the two equal angles are 45. So we're taking an example where we are going to assume that two of the angles are 45. This is because in most of the calculations, we'll actually be working with angles of 30 degrees, 60 degrees, and 45 degrees. So we're going to take an example of 45 degrees. So we actually have this example of an isosceles triangle with the right angle on one side, where this side is equal to 1 and this side is also equal to 1, to make sure that both sides are equal. And then we're going to take the different angles here on the different vertices as being equal to 45. So you can actually see from Pythagoras theorem that 1 squared plus 1 squared is equal to c squared. So if we didn't know what c was, so actually have c squared being equal to 2, because 1 squared plus 1 squared is equal to 2. And then we'll actually have c as being equal to root 3, and that's how we get the hypotenuse here. So we can also see that sine of 45, that means we can actually take any of the two. So sine of 45, remember sine means opposite over hypotenuse. The opposite is 1 and the hypotenuse is root 2. So we actually have sine of 45 being 1 over root 2. Then we also have cos of 45 being 1 over root 2. And how did we get that? Remember, cos is adjacent over hypotenuse, and the adjacent right here is 1 and the hypotenuse is root 2. So it's actually the same thing. So sine 45 and cos 45 are exactly identical. So also have tan of 45 being 1 over 1. Remember, tan means opposite over adjacent. So let's take this 45 for example. The opposite is 1 and its adjacent is 1. So we actually have tan 45, which is equal to 1 over 1 being equal to 1. And that is how we derive the value of tan 45. So this is very helpful, and I encourage you to memorize these. They'll be helpful to you. Alright, so next we're going to move on to trigonometric proofs. Now, this is where we're going to apply the different formulas that we've actually derived. So this is the process of showing two trigonometric expressions to be equivalent. In trigonometry, you'll see complex trigonometric expressions. Often, complex trigonometric expressions can be equivalent to less complex expressions. So this is how we actually prove different identities. So steps for proving trigonometric identities. Step 1, change each term into their sine and cosine equivalents. So actually see how that happens. So in case you're given something complex where it's in sec or in terms of cot or in terms of cosec, so it will actually be helpful if you can change them into their sine and cosine equivalents. So step 2, use trigonometric Pythagorean theorem and other fundamental Pythagorean identities. So these actually include the identities that were actually put in yellow boxes. So these will actually simplify your work. That's why you are encouraged to memorize them. They'll actually be very helpful in this section of proofs. Alright, so next, when working with identities where there are fractions, combine using algebraic techniques for adding expressions with unlike denominators, and that includes an example of LCM. So that will actually be helpful. So step 4, if possible, now this only applies for some numbers. If possible, factor trigonometric expressions. So that means factorization is going to be important in some examples. So let's start off with one simple example. So we're being asked to prove the identity cosec theta tan theta is equal to sec theta. So how do we do this? So we're going to prove it from the left hand side. So we're going to prove that the value on the left hand side can actually bring out the value on the right hand side. So let's prove from the left hand side. So we're going to follow the very first example. So we're going to change all those. So we're going to change the cosec theta and the tan theta into sine and cos to make it easy. Alright, so here's what happens. So actually have cosec theta being the same as 1 over sine theta times tan theta, which is sine theta over cos theta. And then when we multiply the two, we'll actually have this, because sine theta cancels out with this sine theta and will remain with 1 over cos. And remember that we actually proved that 1 over cos is equal to sec theta. And thus, this identity has been proved. And that is correct. Alright, so next, let's move to another example. So actually I have something more complex here, but this is gonna be easy too if we've memorized the different identities. Pythagorean identities we'll actually put in yellow boxes. So from left hand side, so I'm going to prove that the values on this left hand side will actually give us the one on the right hand side. Alright, so we're going to use the alternate form of a Pythagorean identity. Remember that cos squared theta plus sine squared theta is equal to 1. This also means that we can actually take the cos squared theta to the right hand side. What happens if we take the cos squared theta to the right hand side? We'll actually have sine squared theta as being equal to 1 minus cos squared theta. I was doing that because of this value here. Now this actually means we can actually simplify this expression and simply write this as sine squared theta. So we also know that cot squared theta plus cosec squared theta, cot squared theta plus 1 is equal to cosec squared theta. This is also one of the Pythagorean identities that we had actually derived. And then from this we can actually see that this value here can actually be simplified to be cosec squared theta. And that's what we're going to do. So therefore it means we actually have sine squared theta times cosec squared theta, which can actually be equal to cosine squared theta times 1 over sine squared theta. And why is that? It's because we can actually simplify the cosec squared theta to be 1 over sine squared theta. Now we square the sine because the cosec is also squared. And what happens here, we actually see that sine squared theta and this cancel, so we'll actually remain with a 1, and thus we've actually proved this identity. Alright, so let's move on to the next one. Alright, so next we actually have something more complex, but this is also easy, as we will see. So let's solve this. So we're also going to do it from the left hand side. So I want to prove that the value of the left hand side can actually bring out the value on the right hand side. So this is what happens. You can actually, the first step is when we actually have different fractions like this, we get the LCM. The LCM of this and this. So the LCM is this times this. That's why I actually have 1 plus cos theta times sine theta. So I put this in bracket because it actually has a plus sign in the middle. So that not to confuse the different items. And then how do we get this? So when we get this value here, divide by this value here, we actually remain with sine theta. And then sine theta times sine theta is sine squared theta. And then when you also get this value here, divide by sine theta, so they will cancel, the sine theta is cancelled and we remain with 1 plus cot theta. So we actually have 1 plus cot theta times this 1 plus cot theta. And since the two values are identical, it is the same as squaring both of them. So it's like 1 plus cos theta times 1 plus cot theta, which is like the square value of the two. Alright, so what happens next is we can actually open the brackets here. So this can be expanded and we'll actually have it being 1 plus 2 cos theta plus cos squared theta. And then we'll add those values to the sine squared theta. Alright, so next we'll actually collect like terms. We can actually bring this cos squared theta closer to the sine squared theta. And why is that? It's because we actually have an identity, a Pythagorean identity that actually makes sense when you look at the sine squared theta plus cos squared theta. Remember that when you actually bring the sine squared theta plus cos squared theta together, that the two values are equal to 1. And that's why we have this becoming 1. So we'll actually have 1 plus 1 plus 2 cos theta over 1 plus cos theta sine theta. Alright, so next, remember 1 plus 1 is 2, so I actually have 2 plus 2 cos theta over the value below. Alright, so next we can actually pull out the 2 from these brackets and then we'll actually have 2 into 1 plus cos theta. And what do you see? This and this are identical, so the 2 can cancel. So actually have 2 over sine theta. And remember, we actually know that 1 over sine theta is the same as cosec theta. And that's why we have this as being 2 cosec theta. It's because this value here is the same as 2 times 1 over sine theta, of which 1 over sine theta is cosec theta. And thus this becomes true. Alright, so let's move on to another example. So we've been asked to prove this identity: cos theta over 1 minus sine theta is equal to sec theta tan theta. So what happens here? Let's prove from the left hand side. So you can actually see that here we actually have cos theta over 1 minus sine theta. In this example, it only makes sense to rationalize the denominator here. So we're going to rationalize the denominator, and then we'll have this. We'll actually have 1 minus sine theta over 1 plus sine theta. No, actually multiply the 1 plus sine theta we get from rationalizing the denominator onto the numerator, and then we'll actually have this. And then what happens is, when we open this bracket and this, will actually have 1 minus sine squared theta, and then this remains as it is. So remember that this actually makes sense. This reminds me of a certain Pythagorean identity. Remember that 1 plus sine, that cos squared theta plus sine squared theta is equal to 1, and then we know that cos squared theta is equal to 1 minus sine squared theta. So this is actually equal to cos squared theta. It actually makes sense. So as you can see that this and this will reduce, and then we'll actually have cos theta at the bottom. So this is going to reduce, so they will cancel, and then we'll have that value right there. And then what happens is you can actually split this into different fractions. So actually have the cos theta going here and there. And then what happens is this makes sense. Remember, this 1 over cos theta is the same as sec theta. And then sine theta over cos theta is the same as tan theta. And then thus we have actually proved what we actually have on the right hand side. Thus that is proved. Alright, so next we actually have sec 4 theta, sec power 4 theta minus cosec power 4 theta. We actually want to prove that this will actually give us that. So remember that this can be expanded a little bit. Remember that there is a certain rule in algebra. We know that that a squared minus b squared is the same as a minus b into a plus b. So what happens is, if in this case that we have power 4 here, it means if this is equal to 4 and this is equal to 4, it simply means that we actually just have these values here being squared. It actually means that it now applies like that. That's why this value here becomes sec squared theta minus cosec squared theta into sec squared theta plus cosec squared theta. So that's how the expansion works. So we actually are going to transform these and give them values. We're going to express them in terms of cos and sine. So sec squared theta is the same as 1 over cos squared theta minus 1 over sine squared theta, which goes with this. So the same thing happens to this other side, as we can see. Alright, so next we can actually get the LCM here. The LCM here means the product of these two different terms, which is sine squared theta, cos squared theta. And then when you divide this by this, we actually get sine squared theta, which when multiplied by 1 gives you sine squared theta. Then you divide this by sine squared theta, we remain with cos squared theta, which when multiplied by 1 becomes cos squared theta. That's why you actually have this. And the same thing is done here, this being the LCM, and we'll actually come up with that. But remember that sine squared theta plus cos squared theta is equal to 1. So you see where this becomes helpful and it makes sense. So this actually becomes 1. And that's why we actually put the 1 right there. Alright, so what happens next is when we actually multiply this and this, we actually get a power 4. So sine squared theta times sine squared theta is sine 4 theta, and then cos squared theta times cos squared theta is cos power 4 theta. then that's why we actually have this, and thus we've actually proved the identity. All right, so let's move on. Now, that is it for today. So today I'm going to leave you with some trial questions, and these are going to be the identities I actually want you to prove, and these will actually help you to progress faster. So if you can, get time and do these different numbers. So this is going to be the first exercise of this first portion. So this is the end of the very first topic. Alright, and that is it with the introduction to trigonometry. If this video really helped you, feel free to leave a like on the video and feel free to leave a comment to tell me if it was really helpful to you. And then if you're new to this channel, I still remind you to subscribe and then make sure to hit the notification bell so that you get updated every single time I upload a new video. See you all in my next video.